Hi! Before we go on and introduce Newton's third law of motion, let's talk a little bit about the difference between mass versus weight. And there is a difference, even though in everyday language people use those terms synonymously. Even scientists will use weight and mass synonymously because when you weigh something, you'll probably report its mass in pounds or kilograms. Actually, pounds is a weight, kilograms is a mass. But let's look at what is the difference between those two. Scientifically, we define the weight of an object to be the force that gravity exerts on that object. So weight is the force exerted on an object by gravity. So the force of gravity is defined to be an object's weight. And now that we know what Newton's second law is, we know that force is equal to mass times acceleration. And of course, it's net force that gives you mass times acceleration. So if you have an object that you've dropped or thrown, that object is in free fall, and we know that that object is accelerating. So let's just consider the case when the net force on the object is the object's weight. So force is equal to ma, okay, F net is equal to ma. Here, since the object is free falling, the net force on the object is the object's weight, and we know from our experiments with free falling and projectile motion that the acceleration the object experiences, the mass experiences, is the acceleration due to gravity, which is g, where g is 9.8. So technically the weight of the object is the force exerted on the object by gravity. So for example, if you have an object that you weigh and your scale tells you the object's mass is 10.4 kilograms, what is the object's weight? So if I weigh an object and you ask me, hey, what's the weight of the object? I'll probably tell you 10.4 kilograms. But technically, in physical science, the weight really is the object's mass times acceleration due to gravity. That is, the object here in this case, if it has 10.4 kilograms mass, its weight will be that mass times acceleration due to gravity, which we know is 9.8 meters per second squared. And then if everything went right with my calculator, you get the answer that the object's weight is 102 newtons. Now that we understand the difference between weight and mass, let's go ahead and think a little bit about how a scale, like the scale right here, say a bathroom scale that you'd weigh yourself on, or maybe this is an electronic laboratory scale. This kind of scale weighs objects and gives the result in kilograms, but what is the scale actually measuring? A scale like this. Okay, we can put the object on. He gives us the weight, 0.4 kilograms. Scale says that's the weight. And notice here, saying that that's the object's weight is a bit of a misnomer because really it's the object's mass. And is that what the scale is weighing? Is that what the scale understands about the object? Its mass? Well, let's see. What is the scale doing? If I push down on the scale like that right here, notice what happens. I'm pressing down on the scale and the scale's saying that the object weighs 510.6 kilograms, which obviously it doesn't because we know it weighs 0.4 kilograms. So what's the scale doing exactly? And if I took the same scale to the moon, so here you can see the scales on Earth, it's on this nice green lawn right here on Earth. If we took the scale to the moon, where gravity on the moon is 1/6 that of gravity on the Earth, what would the scale say the object weighed then? Would it say 0.4 kilograms? That's the object's mass. If the scale is calibrated properly, then when you weigh it on the moon, it will also have a weight, quote-unquote weight, of 0.4 kilograms. But by weight, in this case, we mean mass. There can be a confusion there because in the speaking language, in the English-speaking language, we do use the terms weight and mass synonymously. But scientifically, they are two different things. Weight is the force gravity exerts on the object, and mass is a measure of the object's inertia. And if it seems like those two concepts are a bit joined at the hip, vis-a-vis Newton's second law, F equals ma, well, absolutely they are. Saying that mass is a measure of inertia almost makes me feel tongue-tied because perhaps mass and inertia are the same thing. Indeed, mass is such a fundamental quantity that it can only be defined in terms of how it interacts with other mass. It only can be defined in terms of how we measure it with things like the scale right here, and not by words. What I mean is that in some sense words just get in the way of the definition. The scale tells you what the mass is, and it gets that value by understanding its force interaction with that mass. That's why this scale, if we took it to the moon, would not read 0.4 kilograms as the weight of this object. It would read 1/6 of that value. That is, it would read 0.066 kilograms. And that's not the object's mass. That's not the object's mass on Earth. The object's mass on Earth is 0.4 kilograms, and the object's mass on the moon is also 0.4 kilograms. This object's mass is 0.4 kilograms no matter what the weight of the object is. If you go into deep space, this object will have 0 weight. There is no force of gravity on it, yet it would still weigh 0.4 kilograms. So how can we understand what this scale is doing? Let's take a closer look. Now that we've defined the weight of an object to be the force that gravity exerts on the object, let's take a bit of a careful look, maybe more careful than you ever thought you wanted to, look at what this scale is doing to measure the weight of our object. By weight here again I mean the object's mass. So that can be a little bit confusing because those terms do get bandied about, jockeyed about, back and forth synonymously a little bit. But there really is a difference. The weight of an object is the force gravity exerts on it, while the mass of an object is its mass, which is a measure of its inertia. So to do this, to figure out what the scale's doing, and I'm going to do it quite carefully, you may already guess what the scale's doing is it's exerting a force on this object, an upward force that's equal and opposite to the force of gravity that the Earth exerts on the object, what the object pushes down on the scale with. But let's do something called a free body diagram. This is something we're going to use a lot. Free body diagram. I mentioned it before. The free body diagram frees the body and draws a diagram. And that is, so here's the body, and by body here I just mean this blue block, 1B. I'm representing him as a dot, and then that dot represents a body, and to that dot, to that body, I draw all the forces acting on him. So what's one force definitely acting on him? Well, there's the weight, there's its weight, which is the force of gravity. So right here, that is the force of gravity. I'll call it Fg, the force of gravity on the blue box. And by definition now, and we know this is how weight is defined, the force of gravity on that box is its weight. We could call it W if we wanted to, W for weight, and that is the object's mass times the strength of gravity. And here maybe I could put a minus sign on it. If I define the down direction to be the minus y direction, then I would have to treat this object as being a negative quantity. The negative tells us the direction it points. In 1D, negative points down if the y direction is defined to be positive up. But this is quite common just to understand the directions are given by the arrows. And here I'm just considering the magnitude of the force, this force vector, which is the weight. Now, this dot represents the blue box. If its weight was the only force acting on it, what would be happening to that object? He would be accelerating. He'd be accelerating with the acceleration due to gravity, g, and we know that on Earth, that value of g is 9.8 meters per second squared. That's the acceleration due to gravity on Earth. And again, if this weight force, this force of gravity, is the only force acting on our box, then we know from experiments, projectile motion experiments and free fall experiments, that this box will fall, ignoring air resistance, with this acceleration. That's just what's going to happen. And that's not happening, it's just standing still right here on the scale. So what's got to be happening? Well, you guessed it, the scale has to be exerting an upward force. The scale has to be exerting an upward force on this box. That's the force of the scale, I'll call it, Fs, force of the scale. Now this box is not accelerating, so what can we say? What can we say about the net force on the box? Well, if we take up to be the positive direction, then the net force on the box is going to be the scale force minus the weight force, force of gravity. And we know that object's not accelerating, so what does that tell us about the acceleration? It's zero. It's got no other choice, because if it's not zero, the object's accelerating. That is the experimental fact of Newton's second law. Okay, so it's pretty simple then. The scale force is equal to the weight of gravity. One minus the other Equals 0 means those two things are equal to each other. So the scale force is equal to the gravity force, which is mass times gravity. Now how's the scale going to go ahead and tell you what the mass is? This scale has to be calibrated to the value of gravity near the surface of the Earth. So near the surface of the Earth, the value of gravity is this value, 9.8 meters per second squared. And that's what this scale is calibrated to. So this scale right here, what is it actually measuring? Inside it's got a spring or some sort of electronic devices inside here that have some kind of way of measuring the force that the scale has to exert. We saw that the scale doesn't really measure the mass of the object. What it's measuring is the force it has to push up on the object with to keep it from accelerating. So remember, when I pushed down on the object, what did I do? I added another downward force over here. I could just throw that on here, F me. And I didn't realize how bad that sounded until right after I said it, but we'll let that go. If we threw that into our equation over here, what would that tell us? That would tell us that the scale force would go up by that amount, because the object's still not moving. Extra forces are acting on it, and it's still not moving. So the scale force has to go up. The scale has to balance. This is force balance. The scale force has to be equal to the magnitude of the downward forces to balance this thing out. So all the scale knows about is what force it exerts. And so the scale designer had to go ahead and divide through by the value of gravity near the surface of the Earth to tell you what the mass is. And then so he'll go ahead and tell you the mass then is equal to, just solve for it over here, whatever the force is you put on me divided by the strength of gravity. And that's why if I took this scale to the moon, the weight force being applied down on the scale would be 1/6 the value that it is on Earth, because the force of gravity is 1/6 the strength of the force of gravity on Earth. So it would say the mass is 1/6 the value that it is on Earth, which is incorrect because the scale hasn't been calibrated yet to Moon's gravity. It would still have the Earth's value right here, and then therefore in that case it would give you an incorrect measurement of the mass. So anyhow, that's about as much detail as we may ever want to go into on understanding the difference between weight and mass. But the important point, the point to take home, is that weight and mass are concepts that are both fundamentally hinged on Newton's second law. That is, Newton's second law, F equals ma. So coming up next, we'll introduce Newton's third law of motion.